The foundational premise of modern telecommunications is the ability to take two distinct points anywhere on Earth and connect them instantly. This diagram shows the required end systems. These are the physical devices generating and receiving the signals, whether it is a traditional telephone processing analog voice or a computer terminal handling digital data. The most straightforward way to establish communication between two of these devices is to run a single, dedicated physical wire straight from the transmitter to the receiver. But that direct link architecture breaks down rapidly as the network grows. 4 devices require 6 cables. 8 devices demand 28. Point-to-point connection scales geometrically. Connecting just 1,000 users requires nearly 500,000 dedicated physical cables. Relying solely on continuous physical wiring cannot scale for global communication. A distinct structural intervention is required to manage the physical load. This illustrates the engineering solution to that geometric cable explosion. The top layout shows the highly inefficient point-to-point network of the late 19th century, while the bottom layout introduces a centralized switching center. By routing every local device to a central hub, the volume of physical cable required to connect a neighborhood drops exponentially. Each end system now only requires a single line to the switch. Operating this hub-and-spoke model requires 2 distinct engineering pillars working together: the physical conduit that carries the signal and the logical architecture that routes it. The physical layer is composed of transmission media. This layer is strictly bound by physics, dictated by bandwidth limits, signal attenuation, and electrical resistance. The logic operates within the switching systems. This hardware and software architecture is responsible for dynamically allocating physical capacity to users on demand. To build a network that spans the globe, engineers must first maximize the amount of data that can be pushed through a shared physical wire. That requires an examination of the physical layer. This flowchart categorizes the available paths for signal transmission. Looking at the left branch, we isolate guided or wired media, encompassing twisted pair, coaxial, and fiber optic cables. The total transmission capacity of these guided paths depend critically on their material properties, the length of the run, and how well the design mitigates signal degradation. When passing electrical signals over copper wire, engineers must fight 2 primary forces: attenuation, which is the natural decay of signal strength over distance, and crosstalk. In parallel copper cables, alternating currents radiate electromagnetic waves that strike adjacent wires, inducing stray interference known as crosstalk. The solution is twisting the wires into a tight helix, forcing emissions into opposite polarities and effectively canceling each other out. Even with interference cancellation, the physical resistance of copper rapidly degrades high-frequency digital signals. To maintain data integrity over a twisted pair, the network requires a repeater every 2 kilometers. To push higher frequencies and broader bandwidth, the physical layer transitions to coaxial cable, shown here in diagram C. It features a solid inner conductor surrounded by an insulator and an outer wire mesh shield. That braided outer shield acts as a continuous Faraday cage. It prevents internal signals from leaking out and blocks external interference from penetrating in, allowing high-frequency broadband signals to propagate over longer distances. Yet, shielding copper only delays the inevitable. As data demands scale, electrical resistance eventually imposes a hard speed limit. Bypassing that limit means abandoning electricity for optical physics. Optical fiber bypasses electrical interference entirely. It transmits data using pulses of laser light fired through a hair-width strand of ultra-pure glass. The light is trapped inside the glass through a physical phenomenon known as total internal reflection, allowing it to travel tremendous distances with almost 0 signal loss. This relies on a strict mathematical constraint. The core's refractive index, N1, must be strictly greater than the cladding's, N2. Early multimode fibers used a wide core, allowing multiple light rays to intersect and bounce, creating interference that degraded the signal. Because of this internal interference, multimode fiber without a repeater is physically limited to 2 kilometers. The solution is single-mode fiber. By shrinking the core diameter to a fraction of a millimeter, light is forced into a single, straight path. By forcing a single path, the internal interference is completely eliminated. This extends maximum repeater spacing to 20 kilometers, establishing the physical backbone for the global internet. Returning to the right branch of our media classes, we find unguided or wireless transmission. This is deployed when running physical fiber across public streets, hostile terrain, or oceans is impossible. Unguided media relies on electromagnetic signals broadcast freely through the atmosphere or the vacuum of space, requiring no physical conduit to guide them. This schematic details a point-to-point link via satellite. A communications satellite operates essentially as a massive microwave repeater stationed in the sky. To remain in a fixed position relative to the ground stations, these satellites must be placed in a geostationary orbit directly above the equator at an altitude of approximately 36,000 kilometers. Operating at that extreme altitude introduces a severe logistical constraint. Transmitting a signal to the satellite and back down requires a round trip of 72,000 kilometers. Even traveling at the speed of light, covering that distance dictates a hard propagation delay of roughly 270 milliseconds, imposed by the laws of physics. While wireless transmission solves the physical reach problem, the speed of light introduces absolute latency limitations. To achieve high-speed instant routing, the core network must return to guided physical media. We have laid the high-capacity optical pipes, but raw physical bandwidth is useless without direction. The network requires a logical layer to route the signals. This diagram demonstrates the basic function of a switch, dynamically connecting an incoming line, or inlet, to the correct outgoing circuit, or outlet. In the early days of telephony, the dominant methodology for managing these connections was known as circuit switching. Under circuit switching, the network establishes a dedicated, unbroken physical path between source and destination before data transmits. Once established, this connection is held exclusively. It physically blocks other signals from accessing that route, generating a busy signal. The mechanical flaw in this architecture is obvious. If the communicating parties pause, or if the line sits idle for even a fraction of a second, the massive bandwidth capacity of the physical cable is completely wasted. Dedicating an entire physical wire to a single intermittent conversation is too inefficient to support global data traffic. The routing logic required a new architecture. The conceptual bridge to modern routing is known as store and forward logic, originally developed for message switching. Instead of locking a physical wire from end to end, entire messages arrive at a switch, are buffered in the hardware's local memory, and are only forwarded when an optimal route opens up. This evolved into the current standard for communication, packet switching. Instead of sending one massive file, the data stream is sliced into uniform, discrete blocks. Each block, or packet, contains a piece of the data payload along with a routing header that lists its exact final destination. Slicing data means millions of packets from entirely different users can be multiplexed over the exact same shared physical medium. The switch's motor role is dynamically reading these headers and firing them to different optimal outlets in real time, without ever locking a continuous circuit. This probabilistic, highly flexible sharing model ensures that the physical cable is never sitting idle. It operates at maximum capacity 100% of the time. Modern telecommunications relies entirely on the synthesis of these two vital engineering domains operating flawlessly together. True universal connectivity is achieved by running the highly efficient probabilistic logic of packet switching over the massive physical bandwidth of single-mode optical fibers.